Okay, so welcome back everybody. We're still on chapter 9, and our general topic here is momentum. But the last thing we talked about before we ended the previous lecture had to do with different types of collisions that are possible. So what we found is that the actual outcome of the collision, how it plays out, does depend on kinetic energy. So in particular, do we lose kinetic energy during the collision, or does the kinetic energy stay the same? That's an important consideration when it comes to a collision. So that idea defines two basic types of collisions we can have. When we have an elastic collision, that means the total kinetic energy of the objects is exactly the same before and after they collide. So we don't lose any of that kinetic energy during the collision. When we have an inelastic collision, there is some loss of kinetic energy during the collision. So in other words, we start off with more kinetic energy before the collision compared to after. So we lose some. But that's just kinetic energy. That's just the energy associated with motion. Remember that overall, energy is something that's conserved. So if we lose a little bit of kinetic energy during a collision, that just means the energy has gone into a different form. Okay, it's gone somewhere else. So it can be converted, for instance, into heat. It can be converted into sound. These are different places that energy might go in an inelastic collision. So if we take a closer look at elastic versus inelastic collisions, we can take a look at these two slow motion videos. And the first one is a golf ball bouncing off of a wall. So when I play the video, just notice that the speed of the ball as it comes in is just about the same as the speed after it bounces off. So its kinetic energy is not really changing all that much. But notice what happens while it's in contact with the wall. So what we see is the ball's coming in, it's moving at some speed, and it briefly comes to a stop while it's actually touching the wall, if you notice that. While it's touching the wall, notice how the ball is compressed, right? It's getting squished along its direction of motion. Now, what's actually happening there is the kinetic energy the ball had coming in is briefly being transformed into what we call elastic potential energy. That's when the ball is being squished. It takes some energy to do that. But as soon as it leaves the wall, it goes back to its original shape. And now that elastic potential energy is kinetic energy again. So if you take a kind of detailed look at what an elastic collision looks like, that's what's happening. The object is being squished, but then it goes back to its initial shape and bounces off. Okay? And if this is an ideal case where we don't lose any kinetic energy at all, then again, there's the same exact amount of kinetic energy going into the collision as it has bouncing back after the collision happens. So, what about an inelastic collision? Well, classic example is a head-on collision of two cars. So let's say these two cars shown in red and white have the same speed, and they hit each other, and they collide like this. Now, notice that basically all of the initial kinetic energy the cars had before they hit is gone. Okay, because they're basically not moving anymore. That means that kinetic energy they had initially has to go somewhere else. Where does it go? Well, like we said, this produces a sound, might produce some heat. Also, if you notice, the cars crumple up, so they become deformed. All of that takes energy. All of that is just different forms of energy that our initial kinetic energy might have been transformed into during the collision. So that's the difference between elastic and inelastic if you take a closer look. Now, the math of elastic collisions can get a little bit tricky, so we're going to stick to a simple case where we have two objects that collide in one dimension. Okay, so this is kind of a lot to take in. We have a two-body elastic collision in one dimension. Okay, let's break that down. Two bodies means there are only two objects colliding, not any more than that. Elastic collision means that the kinetic energy is conserved in the collision. We have the same exact amount of kinetic energy before and after. One dimension means all the motion happens in a straight line. We don't have to think about more than one direction of motion. Okay, so that's what's going on. And what we have here are two equations that we automatically can write down. The first one is a momentum equation, conservation of momentum. This says that the two objects, A and B, have the same momentum before they collide as after they collide. So that equation says MAVA plus MBVB, that's the initial momentum of the system, is equal to MAVA prime plus MBVB prime. That's the final momentum of the system. Okay, if this collision is elastic, then we also have an energy equation saying that the total kinetic energy of these two objects before they collide is the same as after. So that equation says 1/2 MAVA squared plus 1/2 MBVB squared is 1/2 MAVA prime squared plus 1/2 MBVB prime squared. So remember, the prime just means final value. Okay, so as I'm about to show you, I'm going to do a little derivation on the board. If we combine these two equations, which together they look a little intimidating, we get something kind of simple, which is this. VA minus VB equals VB prime minus VA prime. Okay, so before we move on, just want to emphasize the equation you see there in the box, it's only valid if you have a two-body elastic collision in one dimension. That's the only time you should ever be using this. Okay, so let's go ahead and see where that equation for elastic collisions that we just talked about actually came from. How do we arrive at this? So again, we have two starting points. We have momentum being conserved. So we have MAVA plus MBVB equals MAVA prime plus MBVB prime. That is our statement that momentum is conserved when these two bodies collide. What I want to do is take what you see here and just rearrange it a little bit to say that we're going to take all the A terms on one side of the equation, and then we're going to move all the B terms to the other side. So how about we do it this way? Let's take all the A terms, move them to the left side. Let's take all the B terms, move them to the right side. So in order to do that, I'm going to have to first subtract MAVA prime. I already have MAVA here, so when I subtract this term, it'll be common factor MA times VA minus VA prime. Okay, so I moved all the A terms to the left side like I said. I also want to move all the B terms to the right side, which means I'm going to have to take MBVB, subtract that from both sides to move it over here. So that's what is going to give me MBVB prime, because that's a term that's already here on the right side. Subtract VB when we, again, subtract that term from both sides. Let's call this equation 1. And then let's keep going. We also had a second equation which said that kinetic energy is the same before and after the collision happens. So we have 1/2 MA VA squared plus 1/2 MB VB squared is equal to 1/2 MA VA squared, VA prime squared, because now I'm talking about the final velocity, or the final speed, plus 1/2 MB VB prime squared. Okay, so right away, we can make this a lot simpler by just canceling out the 1/2 factor across the board. Also, let's do a similar kind of game to what we did just a second ago. Let's take all the A terms, put them on one side, take all the B terms, put them on the other side of the equation. So how about, just like before, we want all the A terms on the left side, we want all the B terms on the right side. So I'm going to have MA, which is already on the left side, multiplying VA squared. Okay, if I subtract MA VA prime squared from both sides, I move it over here, so now it's negative VA prime squared. That's the left side, because on the right side we have MB times VB prime squared, but we subtract from both sides MB times VB squared to move it over here on the right. So we have minus VB squared like this. All right, so we can actually go a step further with this one. If you see VA squared minus VA prime squared, you should realize that it can be factored out. I can rewrite this as VA minus VA prime times VA plus VA prime. That's how this factors out. Do the same thing on the other side. I have MB, I have VB prime minus VB, and then VB prime plus VB. Okay, now that doesn't look like much, but we're almost done. Let me underline two terms for you. The first term I underlined is MA VA minus VA prime. Where have we seen that before? In equation number 1 right there. That's the exact same thing that's on the left side of equation 1. Over here, the second thing I underlined is MB VB prime minus VB. Again, that's just the right side of equation 1. So these two terms I underlined are equal according to equation 1, which means I can just cancel them out. They're equal. And that just gives me VA plus VA prime, that's all we're left with on the left, equals VB prime plus VB. And so the last thing is we typically write this in a standard form where we put all the terms with no prime on the left. So I'll have VA minus VB, so just subtract this to put it over here, equals VB prime minus VA prime. That's our equation. Again, this is only valid if you have a completely elastic collision between two objects in one dimension. That is the only time you should ever be using this equation right here. Let's take a look at an example. Here is a two-body elastic collision in one dimension. We have a puck, that's the one labeled A, who has a mass of 2 kilograms, and it's sliding along a frictionless table at 12 meters per second. It then collides head-on with a stationary puck, that's the one labeled B, whose mass is 6 kilograms. So given that the collision is elastic, what are the final velocities of the two objects? Okay, so let's look at this example of this two-body elastic collision in one dimension that we saw on the slide. We have two objects, A and B, and we know that momentum is conserved. So we have an equation right away we can write down, which is MA VA plus MB VB equals MA VA prime plus MB VB prime. Let's write down what we know. Well, first of all, MA, that is 2 kilograms. MB, that is 6 kilograms. VA, that's the initial velocity of object A. Well, that was 12 meters per second. Yeah, 12 meters per second. And VB, that's the initial velocity of the other object, was 0. Okay, what we don't know are the final velocities, VA prime and VB prime. That's the goal. Okay, so that's our first equation. It's labeled at 1. Our second equation is what we just derived for elastic collisions. We have VA minus VB equals VB prime minus VA prime. So there it is. So how about we take this second equation and start plugging in numbers that we know. So VA is 12 meters per second. VB is 0. So that equals VB prime minus VA prime. And what we can write then is that VB prime is equal to 12 meters per second plus VA prime. Okay, that's one result we get by looking at this second equation. Okay, cool. Now, let's take that result and actually plug it in to equation number 2. Sorry, equation number 1. That's the one we started with. So when we take equation number 1 and plug in what we know, for instance, that MA is 2 kilograms, VA, that's the starting velocity of that object, is 12 meters per second. That VB is 0, so there's nothing there. And on the other side we have, ran out of space, but on the other side we have MA, which is 2 kilograms, times VA prime. And then what we can do is pop this in for VB prime, because we have plus MB, which is 6 kilograms. And then VB prime, again, we can substitute 12 meters per second plus VA prime. Okay, so kind of a lot going on there, but we're almost done with the problem. So first thing we should note is on this side, on the left, we have 2 times 12, so 24 kilograms meters per second. That's the unit we have. On the other side, I have right here 2 kilograms times VA prime plus 6 kilograms times 12 meters per second is 72 kilograms meters per second. And then we have plus 6 kilograms times VA prime. So notice how I have a unit of kilograms in every single term. Cancel that out. Okay, and then let's simplify some more. We have 24 meters per second here on the left. On the right, we have 72 meters per second from this term. And then I have 2 plus 6, which is 8 times VA prime. Okay, so I'm going to subtract 72 on both sides. 24 minus 72 is negative 48 meters per second. What does that equal? 8 VA prime. So VA prime, just take negative 48 divided by 8. That's negative 6 meters per second. So that negative sign means that object A has reversed its direction. It's bounced backwards. It's moving the other way after collision. Now, VB prime, right up here, we already solved for that. It's 12 meters per second plus VA prime. So I'm going to have to add negative 6 meters per second. What does that give me? 6 meters per second. So how are these things moving after collision? Again, object B, because it's got this positive sign, is moving to the right. Object A has the negative sign. It's moving to the left. And we were able to determine that by thinking of 2 equations. Conservation of momentum and this equation for elastic collisions that we just derived. So we've discussed the idea of conservation of momentum in a lot of detail. We've talked about different types of collisions, elastic and inelastic, and now we're going to switch gears a little bit. Our final topic in this chapter is something called center of mass. So let's get into this. I'd like to introduce you to the idea of center of mass by showing you a video. So what's happening in this video is a person is going to throw a baseball bat into the air, and the baseball bat is going to be set in motion in such a way that it starts spinning. So we have a spinning baseball bat moving through the air, and what's going to happen, if you look at the screen, there's going to be a point on the baseball bat, it's shown in red, that is going to be tracked as the video plays. So take a look at this. Okay, so if you watch this play a few times, there are a few things you should be taking away. First is, if you look at any point on the bat besides the red point, let's say the end of the bat, it's not moving in a simple way. It's kind of moving in a spiral sort of path. But if you look at the red point, okay, there's that point on the bat labeled in red, it's moving in a really simple parabola. It actually just looks like it's moving like a projectile that we normally see would move. So that is just to say that there's something special about that red point. It moves in a different way than the other points on the bat, and we want to understand why that is. So this is our introduction to center of mass. We can divide the motion of an object into two parts. We call these translation and rotation. Translation means the center of mass of the object, and again, that's that point that we saw in red on the previous slide, just moves from one position to another. So it turns out that translation, just an object moving from point A to point B, is caused by forces, right? If you exert a force on something, you can cause translational motion to start happening. And if we want to understand the details of that, we have Newton's laws of motion, right? For example, F equals ma. Another type of motion that we need to consider is rotation. So the object isn't necessarily going anywhere, but it's spinning around its own center of mass. Okay, so as it turns out, what you need to cause something to rotate is a torque. So torques are kind of like force, but for rotation. Turns out there are also equations, kind of like Newton's laws, but they apply to rotational motion. We're not going to talk about rotational motion in this class. That's really a topic for Physics 45, but I hope you can see how center of mass is an important concept, because you can think of the motion of any object as being, again, it's translating, so its center of mass is moving from one place to another, and it's also rotating, it's spinning around. So let's now get into how is it that we calculate the center of mass in the first place. Well, here's what we want to think about. We want to go back to this kind of idea of a system of particles. So we have, in this picture, a system of n particles, that's how many we have. And what are some things we can say about a system of particles? Well, the first thing is we can calculate the total mass. So big M is going to represent the total mass of the system. Well, all we have to do to get the total mass of the system is add up all the individual masses of the particles. So we'll take M1, and then we'll add M2, and then we'll just keep going until we've added all of the masses. The last one we would say is Mn. And if we put this in summation notation, that's a more compact way to write it. It's just the sum of I equals 1 going all the way to n of m sub I. So that's just another way of saying add up all the individual particles and add up their masses, you get the total mass. That's a pretty simple statement. When we talk about the center of mass, this can be thought of as the average position of all of those different particles. But it's not just a simple average that you might be used to. It's something called a weighted average. A weighted average just means if a particle has more mass, it counts more when we take the average. So this is how that sort of calculation is made. RCM, that's the location of the center of mass, is equal to M1 times R1. So it's the mass of the first particle times the position of the first particle, plus M2R2. Again, that's the mass of the second particle times the position of the second particle, and just add all of those up until you get to the last one. Then on the bottom, we're going to take M1 plus M2 and so on, add up all the masses. So that's kind of a lot to say. There's a more compact way to write this. If we take summation notation, we have 1 divided by big M, that's the total mass, because that's in the denominator, multiplied by the sum of I equals 1 to n of mi ri. So we're taking mass times position for all the different particles, adding all of that together, and then dividing by the total mass of the system. Again, this gives you the average position of all of the masses in the system. That's what that really represents. So to give you a more clear sense of what this looks like, okay, I want you to think about this picture I'm showing you here. Okay, we've got 1, 2, 3, 4, 5 different particles in this particular system. And so I draw a little boundary around those particles to say that's my system. And again, if I want to know what the center of mass is, that's sort of the average position of all of those 5 particles. And any position is given by a vector, if you recall, which goes from the origin of your coordinate system to the point in question. So RCM, that position of the center of mass, notice how it's a vector going from the origin to that point, which we call the center of mass. Now, any position vector can be broken up into components, right? There's an X component, there's an X position for the center of mass, there's a Y position for the center of mass, potentially a Z position if we're in 3-dimensional space. So we take this vector equation that we've come up with to calculate the center of mass, and we just break it into those 3 pieces. So for example, if I want to know the X position of the center of mass, I'm simply taking 1 divided by the total mass, 1 over big M, times the sum of mi xi. Okay? If I want the Y position of the center of mass, again, it's 1 over the total mass times the sum of mi yi. Okay, you could do the same for Z if you wanted to. The point is, this breaks into X, Y, and Z components, which you can calculate individually. So you know exactly where the center of mass is, as long as you know where all the different parts of your system are. So this may seem a little abstract. It's actually not so bad once you do a calculation. It's pretty straightforward. So let's do an example right here. We've got 3 masses arranged as shown below. So we have 3 different masses, 5 kilograms, 10 kilograms, and 2 kilograms are the values, and they're at various locations in our coordinate system. We can find where the center of mass of that system is using the equations we just developed. So let's try to work this one out and see how we can utilize these equations. All right, so in this one, we're getting some practice calculating center of mass. And in our system that's shown here, we have 3 different particles. One of them, the one that I'm going to label as mass 1, is located at x coordinate 0 and y coordinate of 1. The second mass, which is over here, has an x coordinate of 1 and a y coordinate of 0. And the last one over here, labeled M3, has an x coordinate of 2 and a y coordinate of 1. So that's where each one is located in this coordinate system. If I want to know what the position of the center of mass is, a good way to start thinking about this is in terms of the x coordinate and the y coordinate of the center of mass separately. So the x coordinate of the center of mass, as we've seen, is 1 over the total mass times the summation of mass times x. Okay? Now in this case, when you see the sum, we should be thinking n is equal to 3. That's how many different particles we have. So it's not really that big of a sum in this case. We're just doing m1 x1 plus m2 x2 plus m3 x3. That's what goes into that sum there. Now, big M represents the total mass of all the particles, which would just be m1 plus m2 plus m3. Now that we've written it this way, it's basically just a big plug and chug, because I know the mass and the x coordinate of every single object in our system. So let's start with m1. Well, that's 5 kilograms. x1, the x coordinate of this guy is 0. Okay, that's the first mass. m2, well, that mass is 10 kilograms. And that x coordinate is 1 meter. Then we have m3, which is 2 kilograms. And that x coordinate is 2 meters. what goes on the bottom? Again, just add the three masses. We have M1, which is 5 kilograms, plus M2, which is 10 kilograms, plus M3, which is 2 kilograms. Okay, if you calculate this, here's what you'll come up with. You'll get 0.824 meters. Okay. Now when we do the y coordinate, it's really the same thing all over again, except instead of x, we have y. So I'll have the mass of my first object times the y coordinate of that, plus the mass of my second times the y coordinate of my second one, and then m3 times y3, all divided by m1 plus m2 plus m3. That's what we need to calculate. And so what this works out to is, again, m1 is 5 kilograms, put that in there. y1, that's the y coordinate of the first mass, is 1 meter. The second mass is, again, 10 kilograms. The y coordinate of the second mass is 0. Okay, then finally we have M3, which is 2 kilograms. What's the y coordinate of the third mass? It's 1. It's 1 meter. Now we're going to take all of that and we're going to divide by just what we had before, the sum of all masses. 5 kilograms plus 10 kilograms plus 2 kilograms. There it is. We do this calculation, and it comes out to 0.412 meters. Okay, so the center of mass, if we write it in xy coordinates, is located at 0.824 meters, comma, 0.412 meters. Let's try to roughly estimate where that is. So my x coordinate is a little less than 1. My y coordinate is a little less than a half. So if I put an x where the center of mass is, it's actually right where I wrote M2. It's roughly over here somewhere. Now notice that it's a lot closer to the bigger masses than the smaller mass. That's how this works. Okay? It's a weighted average. Okay, if something has more mass, it counts more, and the center of mass is closer to those more massive objects. Okay? Okay, so we know that if we have a bunch of different particles, like in the previous example, we can calculate the center of mass of that system of different particles, and it's basically a big sum. We have to just add up a bunch of different terms to get the center of mass. Well, let's think about a solid object, like a baseball bat. You know, we can think of a solid object as a huge collection of particles, right? If you count up all the different atoms that are in an object like a baseball bat, it's an ungodly number, but you can think about it as a bunch of different particles sort of bound together. But realistically, you're not going to do a sum over every single atom in the object. That's just not feasible. That's not a smart way to think about this problem. Instead, the way you do this in practice, if you have a solid object and you want to know where the center of mass of that solid object is you do an integral. We're not going to get into this in this class, how you do integrals to find the center of mass. We will talk about this in Physics 45, so you will eventually have to know how to do this, but for now, we're going to leave it alone. But there is something kind of important to just note here before we move forward. Let's say I have an object with a uniform density. So that just means the density of the object is the same everywhere. It doesn't get more or less dense from point to point on the object. It just has the same density everywhere. If that's the case, then the center of mass of the object is just at the geometric center. So for instance, let's say we have a cube. and it's a uniform density. Maybe it's made out of iron or wood or something, where the density is just the same all over. Well, then you know that the center of mass is just at the center of the cube. It's really that simple. Okay. Now, here's an interesting question. Let's say we're thinking about the Earth and the Sun as our system. That's what we want to know the center of mass of. So the average distance between the center of the Earth and the center of the Sun is about 93 million miles. How far is the center of mass of this system from the center of the Sun? Okay, so all we need to know to calculate this is the mass of the Earth, which is 5.97 10 to the 24 kilograms, and the mass of the Sun, which is 1.99 10 to the 30 kilograms, and again, the distance between them, which is 93 million miles. What we're going to find is, remember, center of mass is a weighted average, meaning if an object has more mass, it counts more. That means the center of mass is going to be really, really close to the Sun, really far away from the Earth. So go ahead and try to make this calculation. Pause the video, see if you can get it, and then we'll go through it. Okay, so in this last example, what we're going to do is calculate the center of mass of the Earth and the Sun as a system. So it's not too hard to do, but you really want to properly set this up. So let's start by drawing the Sun. There's the Sun S. Okay. Now out here, about 93 million miles away from the Sun, we have the Earth. So there it is. Now we want to kind of keep track where things are. So let's draw a coordinate system. And we really only need a one-dimensional coordinate system, i.e. we just need like an x-axis or something like that. So let's call this line here the x-axis. And we can put the origin wherever we want. As you're going to see in a second, it's really convenient just to put the origin right here at the center of the Sun. Okay? So if x equals 0 is the center of the Sun, then x equals 93 million miles, or in scientific notation, we could write this as 93 times 10 to the 6 miles, because a million is 10 to the 6 power. That's the x-coordinate of the Earth. So actually, let's put those in. The x-coordinate of the Sun, that's 0. The x-coordinate of the Earth, again, 93, 10 to the 6 miles. Okay, now we're actually given the masses of the mass of the Earth and the mass of the Sun, which means we can calculate the x position. So where on this line is the center of mass of these two objects? Now we should be thinking that it's much closer to the Sun because the Sun is much more massive, but it's actually surprising how extreme this is. So the x-coordinate of the center of mass is equal to 1 divided by the total mass times summation of mass times x. Okay, now in this case, n is equal to 2. We have two objects. So this is really a pretty straightforward sum to do. On the top, we're going to have the mass of the Sun times the x position of the Sun plus the mass of the Earth times the x position of the Earth. Okay? Just two terms to add up, divided by the total mass of the Earth and the Sun, which is ms plus me. Now, remember I said earlier it's going to be convenient to put the origin right where the Sun is. So xs is equal to 0. That means this first term up here, which has xs in it, is 0. Okay, so let's keep going. The mass of the Earth is 5.97 10 to the 24 kilograms. Now we have to multiply that by 93 10 to the 6 miles. And then finally, we have to divide that by the total mass of the Earth and the Sun together, which is 5.97 10 to the 24 kilograms. Add to that the mass of the Sun, which is 1.99 10 to the 30 kilograms. Now, what's going to come out of this calculation is a distance measured in miles. And exactly what that distance is surprisingly small. We only get 279 miles. So, okay, just for reference, the radius of the Sun, if I'm remembering right, is close to 1,000,000 miles. A little bit less than that, like 700,000, something like that. So the center of mass of the Earth and the Sun is basically right in the middle of the Sun. The Sun is a gigantic object. If you're 279 miles away from the center, you're not that far from the center. So that's what happens when you have a huge disparity in mass between your two objects. Okay, the center of mass ends up being really, really close to the center of one object. So that's it for this portion of the lecture. There's one more part to go through, which will be coming next. And until then, just be safe, be healthy, take care, everybody.